Now, another way we can describe a data set, or more specifically the distribution of data within a set, is using percentiles. And these percentiles essentially give us the position of a point within a set. Now, if we imagine that we have a normal distribution, simply because it's the simplest way to demonstrate this example, and we have a value of 70 located right here on our distribution, and we'll suppose that the area below this value of 70, which represents the proportion or the percentage of points below the value of 70, we'll say this area is 0.4 or 40%. So 40% of our data is below the value of 70. Another way you can say this is that 70 is the 40th percentile. And this concept of the percentile does not depend on a normal distribution or a continuous distribution. You don't have to have a continuous distribution in order to use a percentile. It can be used for any data set. So a percentile can be used for any data set. So now if we generalize, in general, the pth percentile, so p is just a number. In the case where we're looking at the 40th percentile, p is equal to 40. So if we were looking at the 60th percentile, p is equal to 60, and so on. The pth percentile is the point that is greater than p% of the data set. So for example, you already know one of the percentiles, the 50th percentile, aka the median, that would correspond to being the number that is greater than 50% of the points, or in the middle of the data set. And to find this point, in general, we'll say let k be the position of the pth percentile. So if k is 2, that means the pth percentile is at position 2 of the data set. The way we find it, or the way we find k rather, k is equal to whatever p is divided by 100 multiplied by however many points are in the data set, so lowercase n, plus 1. So if you remember, for the median, we found its position by multiplying 0.5 multiplied by the number of points within the set plus 1. So that was a specific case where p was equal to 50 for the 50th percentile divided by 100, which gave us 0.5. Now in the case where you get a decimal as your answer, we'll say that u is the whole number and d is the decimal part. So let's say my answer for this was 4.2, then my whole number part would be 4 and my decimal part would be 0.2. The way you'd find your percentile in that case, your percentile xp for your percentile is equal to the position for the whole number, so the 4th entry in your data set, plus whatever your decimal is multiplied by the difference of the next entry minus the current entry. So x of u plus 1 minus x of u. So this might be a little hard to understand, so don't worry, we're going to do an example that'll make much more sense in a second. But for our specific example for 4.2, we'd select the 4th entry in the ordered set, of course, plus the decimal, whatever decimal we have, so 0.2 in this case, multiplied by the difference between the next entry, so the 5th entry, minus our current entry, x4. And it's very important that all entries come from the ordered data set, just like we had for the median. So now we have an example to hopefully make things more clear. We want to find the 65th percentile for the following data set. So we're looking for the 65th percentile. P in this case is equal to 65. Before we can actually solve, we need to order the set from lowest to largest. So we'll start with 10, then 12, 15, 21, and 22. Then we'll calculate the position of the 65th percentile. So we're looking for K. K is going to be equal to P divided by 100, so 65 divided by 100, or 0.65, multiplied by the size of the data set. So in this case it's 5 plus 1, so 0.65 times 6, or 3.9. So essentially the position we're looking at is 0.9, or 90% of the way from the third entry to the fourth entry. So how do we find that? Our percentile xp, or more specifically x 0.65 for the 65th percentile, is equal to 15 plus 0.9 of the way from 15 to 21. So we'll find their difference multiplied by 0.9. So that's equal to 15 plus 0.9 times 6, and that's equal to 20.4. Therefore, 65% of the data is below the value 20.4. And if our data was strictly discrete, so it can't assume decimal values, you'd round this number up always. So if discrete, 65th percentile is the rounded version, always up. Even if it was 20.001, you'd always round up, because this is the minimum value, where below it is 65%. If we go below this, then below that new value, so below 20, is less than 65%. So we always have to round up. 65th percentile for a discrete data set would be 21. So there's 3 specific percentiles that are used most often, and we give these a special name. They're called quartiles because they break the data into 4 quarters and 4 equal quarters. And so these quartiles, there are 3 of them. The first one, Q1, is the 25th percentile, so sometimes called Q0.25. It is the 25th percentile, and so 25% of the data is less than Q1. Q2 is the 50th percentile, also known as the median. And the third quartile, Q3, is the 75th percentile. And so if we look at our data set, we have Q1, Q2 in the middle, then Q3, and we get 4 equal quarters. Now we also have a name for the range in between the first quartile and the third quartile. So this area is called the interquartile range, IQR for short, and the IQR is equal to the third quartile minus the first quartile. And this value is really important because from it we can get some values that are called the fences. So we have 2 fences, an upper fence and a lower fence. So the upper fence is equal to the third quartile plus 1.5 of the IQR, and the lower fence is equal to the first quartile minus 1.5 times the IQR. So they would be somewhere around here and here perhaps. Or since we have maximum and minimum values, they would be within the data set, perhaps here and here. And essentially these fences, they give us bounds of admissible values. If we have a value within our data set that is beyond these fences, it lies beyond these fences, these values are considered outliers right away. And we'll see why in a second. So the reason we use quartiles, or one of the reasons we use quartiles, is so that we can draw box and whisker plots, sometimes called box plots. And these help us visualize the distribution of our data. So seeing how it's spread, the shape of our distribution, stuff like that. And the way we draw these is that we'll have a graph with two axes. Our x-axis isn't really important. You could have a title for your box plot. So maybe trial 1, because sometimes you might have multiple box plots on the same graph, so you want to label them, trial 1, trial 2, etc. On the y-axis, you have the value that you're measuring. So if I'm looking at heights, I'll have height on my y-axis. And the way we draw the box plot is that I'll draw a line corresponding to the value of my median, or the second quartile. I'll then draw a line corresponding to my other two quartiles, so the third quartile and the first quartile, Q3, Q1. Then I'll draw a box. After that, you'll calculate your IQR, or your interquartile range. So it will be the value of Q3 minus Q1. Then you'll find the positions of your upper and lower fences. So the lower fence is Q1 minus 1.5 of the IQR. So let's say it was about here. And Q3 is, or the upper fence is Q3 plus 1.5 of the IQR. So we'll say that's about here. Keep in mind this is not drawn to scale. Then you'll extend two whiskers from the third quartile and from the first quartile. The third quartile one is going to connect to the maximum value that's within the upper fence. So the max, if you have an outlier, you're not going to connect to that outlier. Anything that's within the upper fence, that's going to be your maximum. And then the minimum value that's within the lower fence, you're going to connect to Q1. Finally, any outliers you have, so values that lie beyond the upper fence, so there's the upper fence, there's the lower fence, any of those values you'll show with stars or circles that are not filled in. And essentially this helps us visualize the spread of our data, since we can see that this is relatively asymmetric distribution, since Q1 to Q2 are pretty close, and the space between Q3 and Q2 is also pretty close. And we can see that the minimum to the maximum also is a relatively equal distance. If you had a skewed distribution, you might see that your median and Q1 are very close together, while the median to Q3 is very far apart, which essentially demonstrates a distribution with a very long right tail. And we can also use this tool to identify and graph any potential outliers. So here's an example to practice drawing box plots. We have the pHs measured by a certain electronic pH meter, and we want to draw a box plot for this data. So these are all pHs. So we want to begin by finding the corresponding quartiles. Before we do that, we want to organize the data from lowest to largest, which it seems like it already is, so that's nice. we'll find the first quartile, Q1, which is equal to the 25th percentile. So its position is going to be 0.25, or 25 over 100, times however many data points I have. So I have 1, 2, 3, 4, 5, 6, 7. So n equals 7 in this case. 7 plus 1. So a quarter of 8, that comes out to a nice number of 2. So Q1 is going to be 6.5. Q2 is going to equal the 50th percentile, or the median. That's going to correspond to a position of 0.5 times 8, or 4. So that's going to be 7. Q3 is going to equal the 75th percentile. So Q 0.75 corresponds to 0.75 times 7 plus 1, or 8, which is equal to 6. And so Q3 is 7.3. So now that I have all my quartiles, I can find my interquartile range, or IQR. The IQR is equal to Q3 minus Q1, or 7.3 minus 6.5, and that's equal to 0.8. So now we can find our fences. So my lower fence, which I'll write as LF, is equal to Q1 minus 1.5 of the IQR. So that's going to equal 6.5 minus 1.5 multiplied by 0.8, and that's equal to 5.3. So that's my lower fence. Any value that is less than 5.3, which we don't have in this set, but if we did have a value less than 5.3, that would be considered an outlier. My upper fence, which I'll represent as UF, is equal to my third quartile plus 1.5 of the IQR. That's equal to 7.3 plus 1.5 times 0.8, and that's equal to 8.5. So any value greater than 8.5, such as this value of 9 within our set, any value greater than 8.5 is an outlier. So this 9, we can conclude, is an outlier, and we likely shouldn't use it for any of our statistical analysis, since it's not really representative of our data set. It's an unusual value. Now if we proceed to draw our box and whisker plot, we'll say this is our pH measurement 1. So this is our first set of pH measurements. On our y-axis, we'll have the pHs. Our minimum value that we're going to have in this set is around 5.0. So we'll put that here. And then we'll reach a maximum of around 9. And I won't fill in the rest, but you probably should if it is for an assignment or a test. But for simplicity and demonstration, we'll just skip to drawing the box plot. So our median is around 7, so near the upper end, or in fact halfway. So we'll draw our line halfway. And then our third quartile is around 7.3, so just slightly above our median. Our first quartile is at 6.5, so just a little more below the median. Then we can draw our box. Our fences are located at 5.3, so a little bit above 5. That's our lower fence. And our upper fence is at 8.5, so a bit below 9. And then our maximum and minimum values within these fences. Our maximum value is 7.3, which is also our third quartile. So in this case, we don't have an upper whisker, which can happen. Our lower whisker is going to go to a minimum value of 6.0, since that's greater than our lower fence of 5.3. We're going to go down to a value, or a minimum, that's going to correspond to 6.0. And then we don't forget to draw our outlier of 9. We'll represent that with a star. And that's all there is to drawing the box plot for this problem.